Section 9.2, we are ready to begin, is L'Hopital's rule. All right. So, when we take limits, and when you've dealt with limits at the beginning of the year, and let's say you were doing a limit and you came out with 0 over 0, then what would you do? You did not run. You stayed with the problem. It's not 1. It's not 1. 42. It was not 42. All right, so, listen up. 0 over 0. Some people want to tell me it's 0. Some people want to tell me it's 1. Some people want to tell me it's undefined. We end up with what is called an indeterminate form when our standard rules collide, and you would have to make a choice as to which one you follow. So 0 over anything is 0. Okay, but anything divided by 0 is undefined. So which rule do you choose? Neither. That's why it's called an indeterminate form, because we don't get to pick which rule we want to use. So when we have this conflict in rules, we end up with what is called an indeterminate form. So at the beginning of the year, when you were learning how to take a derivative and you did it the long way, quite often you ended up with 0 over 0, and then you had to change the appearance of the function you were taking the limit of. You either had to factor and cancel, or you had to multiply by the conjugate to make it look different, and then reevaluate your limit, right? Okay, so not every function is set up so that it's easy to change the limit of. They don't all factor. They don't all have a nice conjugate that we can multiply by. So we are stuck sometimes until this rule comes into play. All right, so we can use L'Hopital's rule when we have one function over another function. That is the first thing I want you to write in your notes. L'Hopital's rule applies when we have one function over another function. All right. Now, if we do not have one function over another function, sometimes we can rewrite the function that we're looking at so that it is one function over another. We may have to change its appearance, but before we can apply the rule, we need to have something like f of x over g of x. The second thing we need to remember is to apply L'Hopital's rule, we need to get one of our indeterminate forms. Which are 0 over 0, and we have them listed over here, infinity over infinity, infinity times 0, infinity minus infinity, one to the infinity, 0 to the 0, and infinity to the 0. There are a few others, but these are the most common ones that we'll run into. All right, so let's look at these first. Why is infinity over infinity an indeterminate form? Infinity over anything is infinity, but when we do anything over infinity, it's 0, or approaches 0, I should say. Infinity times 0, well, 0 times anything is 0. But infinity times anything is infinity. Which rule do we choose? So there is the conflict. Infinity minus infinity. Why would that be an indeterminate form? What's that? Exactly. Infinity is not one set value. Which one is the bigger infinity? We don't know. 1 to the infinity. What do you want that to be? 1. You want it to be 1. But let's think about, if we think about 1 to a power. Let's think about that in the idea of limits from the left and right. So the limit from the left of 1, infinity to the 0. If we think about what is going on around 1, if we're raising it to a gigantic power, if we look at it from the left, if I have 0.999 to the infinity or to a gigantic power, what do I get? I get 0, right? A fraction raised to a power, right? It's going to be really, really tiny. But on the right side, if I have 1.001 raised to a gigantic power, that's going to become huge. Okay, so there's the conflict that we're talking about that happens with 1 to the infinity. That makes it an indeterminate form. All right, so if we are taking our limits and we plug in, which is the first thing we always try to do with a limit, and we get any one of these, then we can apply L'Hopital's rule. Your book gives this first form of L'Hopital's rule, which I'm really going to gloss over because I haven't seen it written this way in other books before. It's kind of interesting, but it's just a special circumstance of the overall rule. So we're just going to work with the overall rule. And the deal is, if you get one of these indeterminate forms, and we have a function over another function, then we can find that limit here is the standard form for our L'Hopital's rule. If we want to take the limit as x approaches a of f of x over g of x, and we get 0 over 0 or infinity over infinity or any of the other indeterminate forms, then all we need to do is take the derivative of the top over the derivative of the bottom and reevaluate the limit. We are not applying quotient rule here. We are not taking the derivative of the quotient. L'Hopital's rule says take the derivative of the top over the derivative of the bottom and reevaluate the limit. So this is what I would like you to get down for the actual rule. So in their stronger form, they say suppose that f of a equals g of a, and they both equal 0. So they're saying we get 0 over 0 when we plug in. That f and g are differentiable on the open interval I containing a, and that g prime of x does not equal 0. So they're making sure that our application of L'Hopital's rule does not have an undefined value by having a 0 in the denominator. All right. So what we have in the cloud is L'Hopital's rule, and that's what we want to apply. So I'm going to go back to our first example. Remember, we have to have f of x over g of x, and when we plug in to evaluate the limit, it has to come out to one of our indeterminate forms to apply the rule. The problem that we run into when students learn L'Hopital's rule is they want to apply it to every limit. But you can't. F of x over g of x, and it has to be indeterminate when you plug in. All right, so let's look at this one. Estimate the limit graphically, then use L'Hopital's rule to find the limit. So when it says estimate the limit graphically, what do? Put it in your calculator and see what the function is approaching as x gets closer and closer to 0. We don't have to do that part right now. I just wanted to remind us what we would do graphically. Now, so when I evaluate this limit, I plug in 0, and what do I get? I get 0 over 0. Check. That means we can use our L'Hopital. That means what we do is we take the derivative of the top, and we take the derivative of the bottom, and we reevaluate our limit. So help me with the derivative of the top. Limit as x approaches 0 of what? Chain rule. We're back in derivatives now.
1 over x squared.
So 1/2, and you're doing it right, Logan. I'm just taking it step by step. 1/2 times 1 plus x to the negative 1/2 times 1, okay? And then the minus 1 goes to 0 when we take that derivative over what? Over 1. All right, and now we just reevaluate our limit. So if I simplify it, it is the limit as x approaches 0 of 1 over 2 root 1 plus x. And that is over 1. That's what you read. All right. So when I plug in 0, what do I get now? I get 1/2. And we are done. That is the limit. Okay? So before this is one of the problems where we would have had to have multiplied by the square root of 1 plus x plus 1 over itself, FOIL the top, multiply the bottom, cancel where we can, and then reevaluate our limit.
So this is like the 1/2. That's actually the limit, not like what slope of the graph is approaching.
Right. It happens to be that if the the ratio of the slopes of the graph are approaching 1/2, then actually the ratio of the actual functions are also approaching 1/2. Okay? Yes.
Why didn't we learn this way originally?
Because you didn't know how to take derivatives.
Okay.
So it has to come a little bit later. And we want the rigor in doing limits in the beginning, of doing derivatives the long way, without jumping right to take the derivative of the top of the derivative of the bottom. Okay. All right. So let's try another one. Actually, this is what you're going to do next. I want you to do this exploration to address what Che just asked about. So I've told you what L'Hopital's rule is. I have not proven it to you. I did not do a formal proof. And I won't take the time to do a formal proof, but this exploration gives you graphical proof that L'Hopital's rule does work. Okay, so let me first tell you what you'll be doing. Our function is sine x over x, and I want you to find, using L'Hopital's rule, the limit as x approaches 0 of that function. Okay, we have f of x over g of x. We can apply L'Hopital's rule without any changes. We're good. Then, in y1, put your sine x, y2, your x, y3, we want to make that y1 over y2, and y4, we want to make it y1 prime over y2 prime. Okay? When you graph it, I only want you to graph y3 and y4. Otherwise, it gets too busy. Okay? So when you graph this in your window, you're only graphing y3 and y4. If you don't know how to turn off the other graphs, call me over. I can help you with that. And let's think about what we're doing. Y3 is the function that we're taking the limit of, correct? And y4 is the derivative of the top over the derivative of the bottom, and we're taking the limit of that. So y4 is our L'Hopital. And what we want to see is, are they both approaching the same thing? Okay? Go ahead, and then you will continue to number 3, and we'll talk about what that is saying once you get that done. Let's go on to a few more examples. We'll come back to this one if we have time. All right, so let's try this one. Now we're going to look at the application of this new rule with the other indeterminate forms. Infinity over infinity, infinity times 0, infinity minus infinity. The first one we're going to work with is infinity over infinity. So at your desk right now, I would like you to apply L'Hopital's rule to solve this problem, and then we will talk. I have graphed my quick little sketches of secant, which is the red curve here. Remember, I always graph a quick cosine curve first. Where cosine equals 0, secant has an asymptote, so that's at pi half. And tangent, which should go through the origin. Just make that a large dot going through there. And at pi half, you can see tangent also heads to infinity. So when we apply L'Hopital's rule, we get secant x tangent x over secant squared. We end up with tangent over secant as x approaches pi half. Well, what's the problem? Not 0 over 0, it is infinity over infinity, correct? All right, well, what would happen if so when this happens, you can apply L'Hopital's rule again. Take the derivative of the top over the derivative of the bottom. But in this case, what would happen? We end up with a secant on the top and a tangent on the bottom. We would still get that infinity over infinity. So in this case, just like in pre-calc, when we are dealing with trig functions, it may make your life easier to go to sines and cosines. So let's see what we have if we change things to sines and cosines. Tangent is sine x over cosine x. Divided by secant would be the same as multiplying by what? Multiplying by cosine. Then we have a nice cancel. We are taking the limit as x approaches pi halves of sine x, which is what? 1. And there we have our solution. But quite often, when we still get an indeterminate form, there is a second layer of L'Hopital's rule and possibly a third layer of L'Hopital's rule. And you'll get a few examples like that as well. Am I okay to leave this screen? Yeah, Joel?
So 1 is the limit?
Yep. 1 is the limit. Anything else on this one? All right, let's look at another one. Yep, example 6 will be our next one. We'll just do 6a. They're very similar. Yes, one is just approaching positive infinity, one is approaching negative infinity. All right, so what is the problem right off the bat with 1a and applying L'Hopital's rule? What are the two conditions that have to happen? One function over another function. Is this written as a function over another function? No. Well, let's plug in. If I plug in infinity here, I get infinity times the sine of what? 0. Because as x goes to infinity, 1 over x goes to 0. So that is infinity times 0. When we get this type of indeterminate form, we need to alter the appearance right off the bat. The limit as x approaches infinity. How can I rewrite this? X times sine of 1 over x is the same thing as sine of 1 over x over what? X to the negative 1, or 1 over x. Does everyone see that? Multiplying by x is exactly the same as dividing by 1 over x. Now I have a function over another function. So when we plug in, we get sine of 0 is 0. As x gets huge, 1 over infinity approaches what? 0. Now we have a 0 over 0. So now we can apply our L'Hopital. Limit as x approaches infinity. Help me with the derivatives, please. Cosine of 1 over x times, no, that would be the integral, negative 1 over x squared. 1 over x is x to the negative 1. The derivative of that would be negative 1 x to the negative 2. That's where that's coming from. Okay? And that all is over what? No, derivative. We've been doing a lot of integrals, I know. Negative 1 over x squared again. And then what happens? We have a nice cancel, yes? And now we can reevaluate our limit. When we plug in infinity, or we think about a gigantic number, As x goes to infinity, 1 over x goes to 0. Cosine of 0 is 1. So, that's a very good example of having to change the look of it to be able to apply L'Hopital. It happens when we get infinity times 0 or 0 times infinity. All right? Let's continue. Number 7 is a great problem, but it is very long and it is very algebraic. I suggest you take a look at it in your book. Okay? If I have time, I'll come back to it, but I want to move on to the next example, which is when we get the indeterminate form of 1 to the infinity, 0 to the 0, or infinity to the 0. All right. So anytime we're taking a limit and we have x in the exponent, when we get our x in the exponent, in any type of math work, what do we do usually to make things easier when we have x in the exponent? We do natural log. All right? So when we end up with this type, if I plug in infinity, I've got 1 plus 0 to the infinity. So this one is 1 to the infinity. That is an indeterminate form. So that's one that we can use. But with this x in the exponent, we want to change the look of it again. And we will use logs to do that. All right, so the first thing we're going to do is we're going to say, let's call this limit L. So we have an equation that we're working with. And then we want to take the natural log of each side of the equation. Okay? My biggest hint with this type of problem is to not forget the left side of the equation. So we have the natural log of L equals the limit of the natural log of 1 plus 1 over x to the x. And I'll make a little note here. The natural log of the limit of something is equal to the limit of the natural log. So that's why my natural log is on the inside. It's another property that's not given in the list of properties. All right, so given that, now what can I do since I'm taking the natural log of this? Bring the x down in front. We still have a natural log of L on the left equals the limit as x approaches infinity of x natural log of 1 plus 1 over x, like that. And I'm going to make my second note over here. Do not forget the left side of the equation. And we take care of the left side as our last step. So we'll come back to it as our last step. All right. Well, now we have this limit on the right, and now it's similar to the problem we just did. We have a function times a function. How can I rewrite that so I have a function over another function? The left stays the same, the natural log of L. The limit as x goes to infinity of what? That's it. The natural log of 1 plus 1 over x all over 1 over x. Well, it's the same idea. If you multiply that by x, it's the same as dividing by 1 over x. Because you multiply by the reciprocal. All right. When we plug in infinity, I've got the natural log of 1, which is 0. and 1 over infinity approaches 0. So we have our situation for let's recall. Okay, help me with my derivative, please. We still have the limit as x approaches infinity of one over, good, Sam, 1 over 1 plus 1 over x times negative 1 over x squared. All of that is over negative 1 over x squared. Don't drop your left side, natural log of L. All right, so we get a nice cancel that happens here. Reevaluate our limit. The limit as x approaches infinity of 1 over 1 plus 1 over x. Well, 1 over x will approach what? 0. So we have 1 over 1. So what does the limit equal? The limit equals 1, but the left side still equals the natural log of L. L is not isolated yet. Here's our last step. E to the power of both sides. So L is equal to E to the first, yep. There is our solution. L is the limit that we were looking for from the beginning. You remember, we renamed that limit L, so that's what we're trying to solve for in the end. So those are our longest ones. Okay? I want you to do one more, similar to that one. Example 9, I want you to try at your desk. Now notice on this one, what you are doing is the limit as x approaches 0 from the right, there's a plus there, of x to the x. My hint for you is to do the problem as x approaches 0 until the very end when you do the limit, and then consider what's happening from the right. Okay? So do the problem as x is approaching 0 until the last step. Then think about x approaching 0 from the right. Okay? So go ahead and get started at your desk. We'll start the same way, L equals